First statement and first reason is going to be the given. In other words, we are claiming that E is the midpoint of DF and F is the midpoint of EG. Step number 2, we're going to use that given, and since it says that E is the midpoint of DF, we can then say that DE is equal to EF, and the reason for that is the definition of midpoint. That's what it means to be a midpoint. Those two segments are going to be equal to each other. Next part of the given says that F is the midpoint of EG. So as I look at my drawing, that means that segment EF is going to be equal to segment FG. Now a note on this one, the reason for that is also definition of midpoint. So I don't have to get another step for this one. It's the same thing, same reason as step number 2. So here is my full step number 2. DE equals EF and EF equals FG. On to step number 3. Now I see that DE is something that I want to try to prove, and I want to end up with FG. Well, DE is equal to EF. Here is that same EF equal to FG. So if I look at this, DE equals EF, which is also equal to FG, I can then conclude by saying DE is equal to FG, and that is a great example of using the transitive property. I was trying to prove that DE equals FG. I have that now, so my proof is over. Statement 1 and reason 1 will be the given. Statement number 2, I want to use my given, although there's nothing I can really do with that right now, but since I've written given, I can put these markings to show that HI and KL are in fact equal to each other. Since I've said it in my proof, I can put the markings. I want to use the proof statement. A segment plus a segment is equal to HJ. If I look at the drawing, I see that the two segments that make up segment HJ are HI and IJ. So HI plus IJ is equal to HJ, and that's a good representation of the segment addition postulate. In the proof statement, it says KL plus IJ is equal to HJ. In the statement that we have HI plus IJ equals HJ. Those two statements are almost exactly the same. The only difference is I want KL, and right now it says HI. Well, if we look back at the given where it says HI and KL are equal to each other, we can then take this HI out, put KL in for it, and we have the proof statement that we want. And the reason for this is substitution. And for the substitution, the equation we substituted into was in step number 2. And the fact where we knew that HI and KL were equal to each other was in step number 1. So in parentheses, we're going to put 2, 1. So someone who looks at this proof can say, well, where did you get this substitution from? We can say we got it from steps 2 and 1. This is what we're trying to prove, so our proof is over. This next proof, we're given AC equals 14, BD equals 14. So after I write down this given, the next thing I'll say is that segment AC is equal to segment BD. Since they're both equal to 14, they're equal to each other, and that is using a great example of the transitive property. Next up, I want to keep this proof statement in mind. I need to have something about AB written down in the proof and something about CD written down in the proof. And I also probably want to use the statement I had before. So as I look at this drawing, I see that AB and BC together make up segment AC. AB plus BC is equal to that. And that is the segment addition postulate, since those points are collinear. And since point B is between points A and C, I can say this using the segment addition postulate. Likewise, I'm going to look at the entire length, the fact that I have BD equal to AC, so I could say that CD plus BC is equal to BD. This segment CD plus BC is equal to the length of segment BD. That's also the segment addition postulate. Step number 4, I'm going to look at what I have in the proof so far. AC is equal to AB plus BC. Those two yellow things are equal to each other. I've got that in my statement from the segment addition postulate. But if I look elsewhere in the proof, I see here is AC as well. It's mentioned again. and we're told that AC is equal to BD. So right now, all of these yellow things are equal to each other. I see BD mentioned down here, so I'm going to highlight that in yellow as well. So these 5 things are all equal to each other. But here's the big step. AB plus BC is equal to AC. AC equals BD. BD is equal to this sum. So since I'm traveling through all these equal signs, starting right here and ending up down there, I can then say that AB plus BC is equal to CD plus BC, and that's another example of the transitive property. A lot of times we only use 3 different objects. This time we have 4. This quantity equals AC, which equaled BD, which equaled that quantity. So those are equal to each other by the transitive property. I'll look at my proof statement. I want to get that AB is equal to CD. I don't quite have that down here, but if I look at the left and I look at the right, AB is on the left, CD is on the right. The only thing is they both have this little BC on both sides. So what we're going to say then is that BC is equal to BC. And when we say that something is equal to itself, the reason for that is the reflexive property, which is kind of the obvious statement. Well, why did we want to say that? That's because on the left-hand side, we're going to subtract BC from both sides to get AB by itself. And on the right-hand side, we're also going to subtract that BC to get CD by itself. So this is a subtraction of steps 4 and 5. Step 4 is where the equation was at. Step 5 is what we subtracted from both sides. And this is what we were trying to prove. So our proof is over. Step 1 and reason 1 will be the given. Step number 2, I'm looking at the given where it says RS is equal to TU. I want to use the given. I'm going to keep the proof statement in mind where it says I want RT equal to SU. So I'm going to try to come up with an equation that uses as many of those segments as possible. Well, one thing I notice is that if I add RS and ST together, that's going to be making up segment RT. That is the segment addition postulate. And in the same step, I'm going to try to bring in segment SU. I want to get RT equal to SU. So as I look at the drawing, there's a couple of segments that make up segment SU. I'll say that TU plus ST is equal to SU. I wrote it in that way on a purpose because it parallels the equation right above it much better. I'm trying to get RT equal to SU. Then on the left-hand side, ST and ST, well, that's the same thing. And I'm told that RS is equal to TU. What I'll do next then is, let's say, rewrite this yellow statement. In the given, we were told that RS and TU were equal to each other, so I'm going to use that fact. And instead of putting TU in here, I'm going to make the substitution and put RS in its place. So taking this yellow equation and putting RS in for TU, keep everything else the same, and we have that equation. This is an example of the substitution property. And we use steps 2 and 1 for that. 2 is the equation. 1 is the fact that we substituted in there. And now I'm going to make a comparison. I'm trying to get that RT is equal to SU. Well, here is RT equal to this entire expression, which is exactly the same thing that we have right here, and that is equal to SU. So I'm traveling through these equal signs. RT is equal to this, which is also right here equal to SU. So then what I can say is that RT is equal to SU, and that is because of the transitive property. This is what I was trying to prove, so the proof is over.